Okay. Good evening, everyone. My name is Nilmoni Karak. I'm a research scholar at IIT Kharagpur. So, yeah, this is I'm a PMRF NPTEL TA for the course Fourier Analysis and its application. So, this is the live season 4, and today we'll review what we have done in last week, and then we will discuss some problem. Okay, so let us start with Fourier transform. Okay, Fourier transform. So what is the definition? Basically, definition is, suppose f is a function from R to R or C, uh, is a function for which f is in L1, means f should be integrable. Okay, then the integral f hat xi equals to minus infinity to infinity ft e to the power minus it xi dt. Uh, so is called, this integral is called the Fourier transform of f. Okay, so why this is needed? Basically, f should be in L1. F should be integrable because if you see when sorry, so this should be make sense, right? So like so this is less equals to, you can say mod ft, right? Mod ft, and this is the modulus is 1. Okay, so dt, this is, this should be less than infinity. So that's why f should be in L1, L1R basically. Okay, okay. So then uh, some examples are there. Okay. Mm, So one easy example is uh, fx. If you take fx is characteristic function minus I to 1 to 1 on characteristic function on the interval minus 1 to 1, then what is the Fourier transform of this? Uh, Minus infinity to infinity chi minus 1 to 1 of t, not yeah, t and e to the power minus I, yeah, so if you take right, f of x, then xt dt, right, and minus 1 to 1 and e to the power minus xt dt, and this is your e to the power minus xt divided by minus it, not it, ix, right, minus 1 to 1. So x and if you write I square multiply by I square, and then I times e to the power minus ix minus e to the power minus ix plus ix. So cos x, this is cos x plus I sin x, this is cos x minus I sin x. Okay, what it will be? Uh, Cos x minus I sin x minus cos x. Uh, so I sin x. Yeah, this is basically 2 sin x. Actually minus. So you can write roughly 2 sin x, 2 by I sin x by x. Hmm. Okay, and yeah, so by definition, like you can calculate Fourier transform, and next Fourier transform of the Gaussian. Gaussian means you know, right? F of t equals to e to the power minus 80 square. So the Fourier transform. So I am not going to prove it. And then Fourier transform of so in lecture video uh, it is already done. Root pi by a e to the power minus x square by 4a. Okay. Okay. And then now we say what is quad space. So definition is this space, the space is consist of all infinitely differentiable functions f of t such that for any mn belongs to natural number, this t to the power m and nth derivative of f of t is bounded. Okay, so one easy example is e to the power minus t square. Okay, so why? Because if you do you if you compute the derivative nth derivative, so roughly it will be like some polynomial times e to the power minus t square, any derivative, and if you multiply with t to the power m, remains it is polynomial. Okay, and then also it is bounded as yeah, because e to the power minus t square is there. Okay, as t tending to infinity, like it is 0 plus minus infinity. Okay. And some properties are there of square space. So number one is ft belongs to S, gt belongs to S, then ft gt belongs to S. Number two is ft belongs to S implies f dash t belongs to S. Alright. And ft belongs to S, and for any polynomial pt implies pt times ft belongs to S. Number four is your f is in S, and one thing, f is in L1, then ft, then f hat t exists. Okay, so for any function which is in square space and which is integrable, so you can calculate uh, the Fourier transform of the function. Okay, and one theorems, if f is in S, then f hat is also in S. Okay, and this is also in a lecture video. So yeah, one more important theorem is your f is in S, then d dt and 1 by I times d dt of ft. The Fourier transform of this is basically xi time f hat xi. Okay, and number two is t times f of t equals to minus d I dj f at j. Okay, so then we have done some Hermits ODE, Hermits ODE, and Hermite polynomials. So recall the Herbert's differential equation. So this is y double dash minus 2x y dash plus 2 lambda y equals to 0. So there are several exercises. Okay, now so yeah, one formula is there for Wronskian. Uh, how to calculate the Wronskian of this differential equation, a solution of differential equation. So this is a constant times uh, exp minus, not constant, basically this is w0 time, because if you put 0 0 constant is nothing but w0, uh, your 2x 2t dt. Okay, okay, now we again move to Fourier transform. So there is a famous theorem, the inversion theorem. Suppose f is in S, then the function can be recovered from uh, its Fourier transform via the formula f of t equals to 1 by 2 pi minus infinity to infinity f hat j to the power, instead of minus e to the power I t j, was e to the power plus I t j and dj. Okay, to prove this identity, the trick is basically you have to use the Gaussian. Okay, okay. So here one exercise analysis prove that minus infinity to infinity f hat j dj equals to 2 pi f of 0. A belongs to S. Okay. So it is already done in lecture. So you can try with this left hand side integral minus infinity f hat xi dxi and put the formula for Fourier transform, and so you will get double integration, and then yeah, the same trick used in the proof of inversion formula, and finally you will get this. Okay. Okay, then we have seen norm estimate for the Fourier transform. So if f is in L1R, then a Fourier transform so this Fourier transform lands up in L infinity. So f hat is in L infinity R. So this is simple, right? So note that uh, this Fourier transform is a continuous linear map from L1R to L infinity R. Hmm. Now, so for this, uh, like for Fourier transform, what is the Riemann-Lebesgue lemma? And just suppose f is in L1R, then f at xi tends to 0 as xi tends to plus minus infinity. Okay. Our next theorem is Parseval formula, also known as Plancherel formula, Plancherel theorem. Parseval formula or Plancherel Plancherel theorem. Suppose Ft and Gt is in S, then as per infinity Ft Gt bar dt equals to 1 by 2 pi minus of infinity f at chi g at chi bar tj. Okay. So from these, okay, no, yeah. Next note: Fourier transform is an operator on L to R. So basically, Fourier transform is a linear transformation from L2 to L2. Okay. So theorem is F is in S, then norm F2 equals to 1 by root 2 pi, norm F at and F the norm 2 of F hat is uh, same as root 2 pi times uh, norm 2 of F. Yeah. Now, one interesting lemma is we studied. Suppose X is a complete metric space and Y is a dense subspace of X and Ty to Y is a uniformly continuous map, then T extend continuously as a map from X to X. Okay, so your X is any complete metric space and Y is a subspace of X. Dense subspace, of course, it should be dense. And Ty to Y is a linear, of course, a linear map and linear operator, and which is uniformly continuous. Then we can extend T from X to X as a continuous map. Okay, and the proof is already done in lecture. Okay, simple. And next, so Fourier transform as an operator on L2R. So So using this result, uh, basically we can extend it as a continuous linear map from L to R onto itself. Okay. Uh, and then convolution of two functions. Okay, what is the definition of convolution? Sorry. Convolution of two functions. Suppose f and g are two absolutely integrable functions on R. That means if g belongs to L1, then their relation f star g is the function defined by f star g r fy gx minus y dy. Okay, and one can check f star g equals to, actually convolution is commutative from g star f. Okay, another important thing is that so this convolution actually plays a role, plays an important role in Fourier transform. Okay, so suppose fg is in S. So f star g actually is defined, and f star g hat xi equals to f hat xi g hat xi. Hmm, okay. Okay. Also one important uh, so heat equation already we have learned heat equation, the heat kernel, right? So ut minus uxx equals to 0, ux comma 0 equals to fx. This is IVP, initial value problem, and this condition is also initial condition. And so using Fourier transform, one can find the Fourier transform of the solution. Okay. Mm, so yeah, one can find basically u xi comma t hat. So this is the Fourier transform of u x comma t. Okay, and f hat xi f hat xi time exponential minus t xi square. Okay, okay. Up to this, we have done in last week. Okay. Now we will see some problem. Some okay, question one. Suppose f is in L1 and alpha lambda belongs to R. Then okay, so then number one, if gx equals to fx time e to the power I alpha x, then what is the Fourier transform g? G hat t equals to f hat t minus alpha. Okay, and other way, if gx equals to f of x minus alpha, then g hat t equals to f at t time e to the power minus I alpha t. Okay, and also if gx equals to f of minus x bar, then g hat t equals to f at t bar. And again, if gx equals to f of x by lambda and lambda greater than 0, then g hat t equals to lambda time f at lambda t. Okay, so let us solve one by one. So first question is basically gx is fx time e to the power I alpha x, then g hat t. We have to compute the Fourier transform of g. So gx is given fx time e to the power I alpha x. So what is g hat t? So this is minus infinity to infinity uh, gx e to the power minus xt dx, right? So now put the value of gx fx e to the power I alpha minus x, sorry, alpha minus t x dx, and now we can write like this: fx time e to the power minus I time t minus alpha x dx, and simply this is nothing but f hat t minus alpha. uh, this is we want to prove. Okay, and what is the next question? Gx is f of x minus alpha, then what is g hat t? So gx is f of x minus alpha. So then what is g hat t? G hat t is your minus infinity to infinity gx e to the power minus I x t dt, right? And I've put the value of g f of x minus alpha e to the power minus I x t dt. Now what should I do? Should I do like x minus alpha equals to y, or dx equals to dy minus infinity to infinity? Okay, f of y and e to the power minus I alpha plus y t dy, and e to the power minus I alpha we can take outside, f of y e to the power minus I y t dy, and this is e to the power oh okay, one thing, sorry, minus I alpha t, yeah, minus I alpha t f hat t. Okay, so g hat t basically e to the power minus I alpha t time f hat t. And next actually, okay, so gx is given as f of minus x bar. So g hat t equals to minus infinity to infinity gx e to the power minus I x t dx, and then just minus infinity to infinity f of minus x bar e to the power minus I x t dx. Okay, then minus x equals to y, so then also just it will remain same, and fy bar and dx equals to dy, so it will be adjusted with this lower limit upper limit. Okay, and e to the power I y t dy. Okay, and we write like this, minus infinity fy and e to the power minus I y t dy whole bar. Okay, and then this is f hat t whole bar. Okay, this is also done, and last gx is f of x by lambda, your lambda greater than 0, so g hat t lambda f hat lambda t. This is what we have to prove. Okay, okay, now g hat t equals to minus infinity f of x by lambda e to the power minus x t dx. Similarly, x by lambda equals to y minus infinity to infinity f of y. So x is your basically I lambda y t, and dx is lambda time dy. So this is lambda time f hat lambda y. Oh, this is y. Okay, this should be fy and lambda y. Okay, that's done. Okay, now next question. The next question is simple. Suppose f is in L1 and f is positive, so that the Fourier transform of y, the modulus of the Fourier transform of y is strictly less than f at 0 for all y not equal to 0. Okay, solution. Okay, so let us solve this. And for all y belongs to R, it is true, right? Mod of f of x e to the power minus xy, this is equals to your mod of fx, and f is positive, so that's why f is mod of fx is fx. And so from here fx e to the power minus x ixy, this is in L1. Since f is in L1, now let us compute the what is f at y, and this is basically modulus minus infinity to infinity f of x minus I xy dx. So this is less equals to minus infinity to infinity and mod fx, but fx is positive, so only fx, and the modulus is this. So modulus of this equals to fx, so dx. And this is you can write minus infinity to infinity fx e to the power minus I times 0 times y dy, right? So this is basically f at 0. So your f at y less equals to f at 0 for all y belongs to R. But for non-zero y, we have to prove the inequality is strict. Okay. So if possible, let f hat y is strictly equal, sorry, exactly equal to f at 0 for all for y not equals to 0, for y not equals to 0. Okay, now so this is equal, right? So use the definition minus infinity uh, fx e to the power minus ixy sorry, dx, and equals to minus infinity to infinity fx dx, and this is equals to, you can write minus infinity to infinity mod of fx e to the power minus ixy dx. Okay, this is hold, right? This star is hold, but so there is a theorem, right? Real analysis also. So the theorem is, so this whole modulus of this integral equals to this integral of modulus of this integrand function. When it is happened, we have, so theorem is basically, suppose f is in L1 mu and f d mu mod f t mu, then there exists a constant alpha such that alpha time f equals to mod f almost everywhere on x. Okay, so similarly, using this theorem, we have there exists a constant alpha such that alpha time fx time e to the power minus ixy equals to mod of fx e to the power minus ixy. Okay, and this is equals to nothing but mod of fx, and this is equals to fx because fx is positive, and this holds only for almost everywhere on R. And since fx is positive, alpha time e to the power minus ixy equals to 1 almost everywhere on R. And when it holds only when y equals to 0. But we assumed y not equals to 0, which is contradiction. Okay, so hence our assumption is wrong, so that for all y not equals to 0, it is done. Okay, now let us calculate okay, now uh, let us see the next problem. I hope it is clear. Okay, so calculate the Fourier transform of the characteristic function of the interval close interval AB. Then for n belongs to natural number, let Gn chi minus n to n. Okay, and h equals to chi minus 1 to 1, and compute Gn star h. Okay, also so that your Gn star h is the Fourier transform of a function fn belongs to L1, except for a multiplicative constant. Fn x sin x sin nx divided by x square. Okay, okay. Let us solve. First question, we have to find the Fourier transform of this function. Okay, Just use definition. It is very easy. Uh, T minus infinity to infinity chi a b x e to the power minus I x t dx. Okay, and you know the definition of this. So in the interval, this takes one, and uh, in the interval outside the interval, it takes zero. So a to b e to the power minus I x t dx, and this is you can write it e to the minus e to the power minus IVT minus e to the power minus IAT. Okay, if t not equals to 0, but if t equals to 0, then only b minus a. Okay, t equals to, sorry, t equals to 0. Okay, so this is the Fourier transform of chi ab. Okay, now in second problem, gn is chi minus n to n, and h is chi minus 1 to 1. Now similarly use gn star h, and this is 1 by, sorry, so what convolution formula, the definition is there is no constant, right? Yeah. Okay, so the definition is basically your minus infinity to infinity. So g is your chi minus n x minus y, and chi minus y dy. Okay, and this is equals to minus 1 to 1, because n is in natural number, so n can be 1 2 3 and so on. So the interval where the whole thing holds, so this is minus 1 to 1. Okay, yeah, otherwise this is like uh, in the outside and in the outside the interval minus 1 to 1, this takes 0, so that's why the integration should be minus 1 to 1, and chi minus n x minus y dy. And now what is the value of this integral? This is basically length of the, so you, if you use Lebesgue measure, okay, so your y runs from minus 1 to 1, and this is basically measured of so y, okay, x minus n to x plus n intersection minus 1 to 1. So the measure of this interval. Okay, so there are several cases. Okay, okay. So if, so we don't know like the ranges of x. Uh, so in the different ranges of x, we will have different value. Okay, so x less equals to minus n minus 1. That is uh, okay. So basically, see one thing: minus 1 less than x minus less equals to x minus y less equals to n, and y lies between 1. Okay, minus 1 to y minus 1 less equals to x less equals to minus 1 less equals to y less equals to 1. So yeah, so first case 1, x less equals to minus n minus 1. Yeah, outside the interval. So basically that is x plus n less equals to minus 1. So this is outside the interval, right? So measure should be 0. Measure should be 0. Case 2, minus n minus 1 less equals to x less equals to minus n plus 1. Okay, and that is basically x minus n less equals to minus 2n plus 1, and the okay, and the minus n, upper bound of minus n is minus 1. So minus 2 to minus 2 n plus 1 is minus 1. Okay, and so x minus n less equals to minus 1. Now the measure is x minus n x plus n intersection minus 1 to 1. The lower limit of this is minus 1. Okay, so this should be x plus n minus 1 minus 1. Simple the length of this interval. Okay, because the this is basically intersection is from minus 1 to x plus n. This is same as measure minus 1 to x plus n. Okay, so x plus n plus 1, right? And case 3, minus n plus 1 less equals to x less equals to n minus 1, and that is x plus n greater equals to 1 and x minus n less equals to minus 1. So minus 1 to 1 contained in x minus n to x plus n. So intersection is basically here minus 1 to 1. Measure x minus n to x plus n intersection minus 1 to 1. This is the basically 2 because the intersection is minus 1 to 1. And now if n minus 1 less equals to x less equals to n plus 1. Then x minus n greater than minus 1 less equals to 1. Okay. And what about x plus n less equals to 2n plus 1 or greater equals to 2n minus 1, and 2n minus 1 is greater equals to 1, and yeah, this we cannot bound for large value of n. So that, okay, we have to go to next page. Hmm. So in that case, measure is x minus n x plus n intersection minus 1 to 1 is so your what we have x plus n greater equals to 1, and yeah, so this is 1 minus x minus n, so 1 minus x plus n. And last, case 5, if x greater equals to n plus 1, then x minus n greater equals to 1. So yeah, here so x minus n greater equals to 1. So the intersection is phi. Measure of intersection is phi. So this is measure, the measure is 0. Okay. So finally what we get, gn star h of x equals to, okay, 0 x plus n plus 1 to 1 minus x plus n 0. Your x greater less equals to minus n minus 1 minus n minus 1 plus n minus n plus 1 less equals to x and n minus 1 and sorry minus n, no, n minus 1 to n plus 1 and 0 x greater equals to n plus 1. Okay, this is gn star h, but this is the like Fourier transform of a function fn. Okay, so here like some constant time fn hat equals to gn star h, and fn is your sin nx by n x times sin x by x, so you can write this. Okay, and first we claim that each fn is in L1. Now one thing, sin x by x goes to 1 as extending to 0. Okay, so we define, if we define fn0 is n, then fn is continuous on R. Also, this fn is yeah, particularly bounded by a constant on the interval -1 to 1. Fn is bounded by mn on -1 to 1. Okay, and what about mod of fn x less equals to 1 by x square if mod x greater than 1, right? Greater than 1. So we have now R fn. So yeah, why we are like interested to show fn is in L1, because so to like confirm fn has a Fourier transform, it should be in L1, right? uh, fn x dx equals to mod x greater than 1, greater equals to 1, or greater than, you can write fn x dx plus not fn x, so you can write instead fn t dt, and mod x less equals to 1 fn t dt. Okay, mod also is there, and this is less equals to 1 to infinity. Okay, uh, so fn x is for this interval the less equals to 1 by x square. So 1 to infinity 1 by t square dt plus minus into minus 1 1 by t square dt plus and it is bounded by mn, so yeah, 2 times mn, right? -1 to 1 mn. Okay, so this is 2 times 1 plus mn, and this is bounded, so this is less than infinity. So finally fn is in L1 for all n belongs to natural number, sorry, natural number, right? Now what we will do, now let us see how gn star h hat is basically some constant times fn. Okay, okay, so now gn comma h belongs to your L1, right? So we already have seen Gn star H hat equals to Gn hat star H hat, right? Now what is Gn chi minus n to n? So what is Gn hat? Already we have seen, right? So what is the chi a b hat? Okay, so from there, uh, yeah, we can write. So here a equals to n, b equals to n, a equals to minus n, b equals to n. So yeah, so this is basically minus e to the power minus int minus e to the power int by it if t not equals to 0 and 2n, n is n and minus n, so if t equals to 0 and after simplification, so e to the power nt minus int, so this should be 2 sin nt divided by it if t not equals to 0 and 2n if t is 0. And what about h? H is your chi minus 1 to 1. So what is h hat? H hat is, so instead of n just put 1, 2 sin t divided by it if t not equals to 0 and 2 if t equals to 0. Okay. Hmm. Now, what is Gn star H hat? So this is like we can multiply, right? Gn hat star. This is same at Gn hat star H hat. Okay. So 2 to 4, 4 times sin nt. Uh, one thing. Okay, 4 sin nt and sin t I square t square if t not equals to 0 and 4n if t is equals to 0. So this is some constant times. Yeah. So minus 4 sin t sin nt sin t by t square t not equals to 0. Uh, so and for n t equals to 0. Okay, so now this is basically your fn fnt. Okay. What we wanted to prove. And next question, question 4. This Fn, norm of Fn, norm 1 of Fn goes to infinity as n tending to infinity. How? Okay. Okay. So this is 2, right? Sin x by x greater than 2 by pi when 0 less than x less than pi by 2. So one can do this using mean value theorem. How? So fx is your sin x. Fx minus f0 divided by x minus 0 equals to f dash y, right? So this is sin x by x equals to cos y. Okay. So sorry, this is sine graph. So from this to pi by 2. Okay. So maybe it can be done with the other way. Okay. Now let us keep it. Anyway, this is basically greater than 2 by pi. Okay. And anyway, okay. Okay. So mod of sorry, norm fn1, norm 1 of fn is basically infinity infinity mod fnx dx. Okay, so sin x by x goes to 1 as x tending to 0, and also hold at x equals to 0 this inequality, right? So mod of fnx greater than 2 by pi times mod sin nx divided by x. Okay, so from this greater equals to 2 by pi integration 0 to pi by 2 sin nx by x modulus dx equals to 2 by pi 0 to n pi by 2 mod sin x. So just this is a change of variable, okay, dx, and it is well known that 0 to infinity mod sin x by x dx greater equals to sum k equals to 0 to n integration k pi to k plus 1 pi mod sin x by x dx. This is greater equals to sum k equals to 0 to n. Yeah, the what is the lower bound of, not a lower, upper bound, yeah, so lower bound of 1 by x, so this is k plus 1 pi, and integration k pi to pi mod sin x k plus 1 pi dx. This is equals to this is equals to your 2, okay, 2 by pi is there, 2 by pi and this sum. So the integration is basically gives 2 and k equals to 0 to n 1 by k plus 1, and this goes to infinity as n goes to infinity. So finally 1 goes to infinity as n goes to infinity. Okay, what's the next problem? And this is the final problem of today, and question 5, maybe 5, right? Yeah. Suppose f is in L1 and f is differentiable almost everywhere, and f dash is in L1. Okay, the question is, oh sorry, does it follow that the Fourier transform of f dash is ti f hat t? In general, this is not true. So f should be in square space, then it is true. Okay, anyway, given counterexample, no, in general, so take f equals to chi. Okay, then f is in L1, no doubt, right? The integration is 2, so this is positive. And what is f dash? F dash is also 0 almost everywhere. Yeah, so actually f is not differentiable at the point -1 and 1, and in the rest interval f is differentiable, and so that's why f dash is 0 almost everywhere on R except 2 points. Okay, so f dash belongs to L1 almost everywhere on R, almost everywhere. Okay, uh, yeah, no issue. So now f dash t hat equals to minus infinity to infinity f dash x e to the power minus ixt dt. Okay, and what is f dash? F dash is 0, right? F dash is 0, so this is 0 almost everywhere on R. Okay, now just compare with now ti f hat t equals to ti minus infinity to infinity fx e to the power minus xt dx. Ti, so fx is your minus 1 to 1. Okay, 1 to 1, e to the power minus ixt dx. This is basically ti times 2 sine t divided by it, right? Ti. So ti cancel. This is 2 sine t, and this is not equals to ti time f hat t, because f hat t is, this is ti times 2 sine t by t. This is I sine t, not, okay, this is 2i sine t, not 2 sine t only. Okay, okay, this is the counter example. I hope it is it is understandable and you got this. Okay, so today I stop here, and uh, yeah, we will meet in the same time on uh, 22nd February. Okay.